share your screen? If you could share your screen.
Actually, on my end, it shows that I am sharing my screen now.
Oh, yes, you're right. And I'm seeing it. I forgot to how this works. So please continue.
Thank you very much. I want to thank Meredith for hosting this event and actually creating with other people together this platform for us to all share our results online. So I'm going to talk about some work that we have done over the last few years on the singular flows. So let's quickly set up the stage here. So in general, hold on, there's something wrong with my. Okay, there we go. Uh, huh. There's something wrong with my like. Okay, so we're looking at a compact Riemannian manifold, and we assume that there's no boundary of it. And then given a C1 vector field, we say that a point is a singularity if at that point the vector field is simply the zero vector. And we're going to denote by this notation SING of x, the set of all singularities. Now, the reason that we want to look at this kind of vector field is because, first of all, they exist on all manifolds, unlike non-singular vector fields that can only exist on certain very special manifolds with a very specific topological structure. Like, for example, if you look at a Nassau vector fields on surfaces, the only type of surface that support those kind of vector field are those where the Euler characteristic is zero, right? Um, Now, we want to note that if you have a singularity in your vector field, then the vector field cannot be uniformly hyperbolic because being uniformly hyperbolic requires you to have the invariant splitting. And in particular, you want to have a three-way splitting into three bundles, the stable bundle, the unstable bundle, and the bundle generated by the flow direction. But normally, hyperbolicity forces this splitting to be continuous. However, if you have a singularity, the flow direction does not exist at those points, and therefore the splitting cannot be continuously extended to those places of the vector field, and therefore your flow cannot be uniformly hyperbolic. So then the very first question people want to answer is how do you describe hyperbolicity when you know that they cannot be uniformly hyperbolic? So this question turns out to be extremely difficult and was only answered in the last couple of years. But this question actually started in the very early days of dynamical systems, going all the way back to the 1970s and even maybe 1960s. So back then, when people were studying the stability conjecture, they defined the so-called star property. They said that a vector field is a star vector field if there exists a C1 small neighborhood of the vector field, so that for all vector fields in this small neighborhood, all the periodic points and all the singularities are hyperbolic individually. So for periodic points, that means you have the three-way decomposition along the orbit. And for singularities, it's just that the singularity is a hyperbolic fixed point for the time one map. So you can define the same way the star diffeomorphisms. Those are diffeomorphisms where under perturbation, all the critical points, sorry, all the periodic points and all the fixed points are hyperbolic individually. And the reason that the star property is important, actually, let's skip this page. The reason the star property is important is because it's actually an intermediate step in the proof of the stability conjecture. So in the 1960s, Smale proved that if you have uniform hyperbolicity plus some sort of transversality condition, then your system is structural stable. This is something that we now teach at the in our smooth dynamical system courses. But then the question is, if your system is structural stable, does it need to be hyperbolic? Well, the answer turns out to be yes, but the proof is extremely hard, and usually it consists of two steps. The first step is to show that structural stability implies the star property. This is actually done by John Franks in 1971. The proof is actually quite easy. You assume that you don't have the star property. That means under perturbation, you can create a neutral periodic orbit. But being a neutral periodic orbit will allow you to do small perturbations to make it either a contraction or expansion. And then therefore your system cannot be structurally stable. So this part of the proof is relatively simple. But then the hard part is to prove hyperbolicity from the star property. Now the star property is really non-uniform because it only tells you that under perturbation all the periodic orbits are hyperbolic individually, but you don't have any uniform control on the expansion or contraction rate or anything like that. Therefore you don't know if this kind of hyperbolicity can be carried over to the closure of the periodic set. So for diffeomorphisms, this was proven by Chantal Liao in 1980 for surface diffeomorphisms, but it was also proven by Manier in 1982, just 2 years after, for surface diffeomorphisms. And then Manier proved the general case in 1988 that in all dimensions, star diffeomorphisms are actually uniformly hyperbolic. But then how about vector fields? Well, the question for vector fields become a lot more complicated. So the first breakthrough was done for vector fields without any singularity. This was carried out by Hayashi and by Gan and Wen around 1998 to 2003, I think, in a sequence of papers that showed that if your vector field does not have any singularity and it is a star vector field, then it must be uniformly hyperbolic. The proof actually uses a very different strategy when compared to the case of diffeomorphisms. Vector fields tend to make things a lot harder than diffeomorphisms, even if you don't have singularity. But when you do have singularity, well, the question becomes a lot more complicated. In this case, your system cannot be uniformly hyperbolic, so what are we even talking about? Well, um, Gan and Wen proved in around 2014 that when you have singularities and when those singularities have the same stable indices, here the stable index is the dimension of the stable space of those singularities. And in this case, they showed that the vector field is sectional hyperbolic. And the sectional hyperbolicity was actually introduced by a bunch of people around year 2000 to characterize the hyperbolicity of the famous Lorentz attractor. And originally, they had only this one example, the Lorentz attractor, but then later it was actually proven by Shi, Gan, and Wen that this is actually a very robust phenomenon and always characterizes vector fields whenever you have singularity of the same indices that are star. But then, of course, the next question is to ask what happens if you have singularities where the dimension of the stable space the dimension of the stable space are different. Well, for a long time, people actually conjectured that this case cannot happen because they kind of have this idea that if you have singularities of different indices, you may be able to just create a periodic point where you go from one singularity to another and back and forth so that and having different indices may create a periodic orbit where the dynamics is neutral. So this will violate the star property. This is what people try to do for a long time. But actually, it was shown just a few years ago that this phenomenon can actually happen robustly, and they actually proposed a new version of hyperbolicity to characterize this phenomenon. And Bonatti and Daluz showed in 2021 that the star property is equivalent to what they call multisingular hyperbolicity. And the multisingular hyperbolicity actually contains a large family of examples, including the traditional Lorentz attractor, but also includes a lot more systems than the Lorentz attractor. So what is multisingular hyperbolicity? Well, the definition is extremely complicated. The basic idea is that when you look at vector fields, you don't really like the direction generated by the vector field because you don't have any contraction or expansion along this direction. And for us who work on non-uniform hyperbolicity, we like expansion and contraction. Therefore, the vector field direction is actually going to give you some problem. And therefore, the idea is to take a quotient over the vector field and to create something called the normal bundle of the manifold. So basically, you're looking at the vector bundle that is the orthogonal complement of the vector field. This is a subbundle of the tangent bundle, and you define a flow that acts on the normal bundle by projecting the actual flow to the normal bundle via just the orthogonal projection. So that's the so-called linear Poincare flow. And then once you have the linear Poincare flow, you can describe hyperbolicity on the normal bundle. And this is actually done in a very convoluted way. Roughly speaking, they want the normal bundle to have some kind of a splitting that is invariant and dominated. And also on the normal bundle, they want to see exponential contraction and also exponential expansion when you iterate those vectors using the linear Poincare flow. So the idea is that when you look at vector fields, you don't really want to look at its action on the tangent bundle because of the lack of contraction and expansion given by the flow direction, but rather you want to do some kind of quotient, and hopefully from there you can obtain hyperbolicity in some sense. So that's sort of the idea. Uh, Now, so far we have three versions of hyperbolicity. They're uniform hyperbolicity when you don't have any singularity. Oh, hold on. So, and you have, oh gosh, this is so hard to navigate. Uh, there's something wrong with the way that the pages go. So whether I press left or right, they always bring me to the previous page for some reason. Oh gosh. I go page 10 over here. Oh, technical difficulties. Yes? Okay, now it's working. Okay, so we have sectional hyperbolicity, which is also defined on the tangent bundle, but roughly speaking, you take the direct sum of the flow direction with the unstable direction to create basically a center unstable bundle. And there's also the multi-singular hyperbolicity that is defined on the normal direction instead of on the tangent bundle. The relation between them is that everything that is uniformly hyperbolic must be sectional hyperbolic. Anything that is sectional hyperbolic must be multi-singular hyperbolic, and the last one is equivalent to the star property, which means the last one is the one that we should look at. So this is basically the end of the story for hyperbolicity. But then you want to look at the topological structure and going actually all the way back to the work of Stephen Smale. He proved in the 1960s that when your system is uniformly hyperbolic, you can write the non-wandering set into a finite disjoint union of hyperbolic basic sets. And now when you want to study uniformly hyperbolic systems, you study their properties on the hyperbolic basic sets. And because you have only finitely many of them, therefore you can recover the same property for the entire space. Now, for vector fields, it actually is a conjecture nowadays whether you have the same behavior for star vector field. So the conjecture says for any C1 star vector field, the non-wandering set decomposes into a finite disjoint union of compact invariant set, each of which is the homoclinic class of a hyperbolic periodic orbit, and they're isolated. So this is still actually unknown nowadays, and it's one of the biggest conjecture for singular vector fields. Now, let me show you our main results that we worked on for the last basically decade. What we have proven is basically a version of the decomposition conjecture from a ergodic theory perspective. So when you look at ergodic theory, you want to look at invariant measures, and in particular, you want to look at the so-called equilibrium state and measure of maximum entropy and so on and so forth. But before any of that, you want to show that your system is actually chaotic in the sense that it is sensitive to initial data. This is known as expansivity. And this may surprise you, but actually expansivity for even like hyperbolic singular flows were previously unknown. And we proved in 2025 that every multi-singular hyperbolic set is actually robustly expansive. And therefore, their metric entropy varies upper semi-continuously, and therefore all equilibrium states for any continuous potential must actually exist. Now, the next work, once you have the existence of equilibrium state, is to establish the uniqueness. And actually, again, this may surprise you, but for over 60 years, the uniqueness of the measure of maximum entropy for the Lorentz attractor is actually unknown. And we proved that in 2024 in our previous paper. So we showed that if you have a sectional hyperbolic attractor with some very weak topological condition that includes the Lorentz attractor, then there exists a unique equilibrium state for every Holder continuous potential, and in particular, there is a unique measure of maximum entropy. So all the topological conditions here are actually C1 open and dense, and they can be verified for specific systems. And we did this general framework first, and we actually verified it for the classical Lorentz attractor. Um, then we have a much stronger version of this result, basically improving the result from hyperbolicity from sectional hyperbolicity to multi-singular hyperbolicity, where you basically don't know anything about the topological structure of the flow because that definition was only like discovered in 2021. It's still a very new and ongoing field. So this is a quick comparison between sectional hyperbolic attractors and the multi-singular hyperbolic sets. You can see that there are some common properties in the sense that they all are isolated, they all contain periodic orbits, but when it comes to more subtle topological informations like the existence of invariant foliation, the robust transitivity, and the nearby dynamics, basically nothing is known at this point. Um, so now let me show you some corollaries of our main result. So previously, remember, the conjecture was to show that every star vector field has only finitely many homoclinic classes. And then think about how we prove that every like uniformly hyperbolic flow has only finitely many measure of maximum entropies. You first use Smith's decomposition theorem to say, oh, there are only finitely many hyperbolic basic sets. And then you use the work of Bowen to say that on every hyperbolic basic set, there is only one measure of maximum entropy. And because you have only finitely many hyperbolic basic sets, therefore the system has only finitely many measure of maximum entropies. So this is a very classical way of proving the finiteness of equilibrium state, and you can actually teach this at your graduate level smooth ergodic theory course. But then to show something similar for vector fields is a completely different story because you don't have the spectral decomposition theorem. It is still a conjecture. So the idea for us is to actually prove the existence of, or sorry, to prove the finiteness of MMEs first, and then use that to show the stable the decomposition conjecture. And we were actually able to do this to a certain extent. So we proved, first of all, that C1 open densely every star vector field is expansive, and in particular, you always have equilibrium state. And then in a much harder, like with a much harder proof, we were able to show that C1 open densely every star vector field with positive topological entropy can only have finitely many ergodic measure of maximum entropies. And actually, there is a more general statement where you can show that you have only finitely many equilibrium state for every Holder potential. And all this is done without knowing that you have only finitely many Cherenkern current classes or finitely many homoclinic classes. And then using the finiteness of the measure of maximum entropy, we prove the following version of the spectral decomposition conjecture. So we showed that for C1 open dense star flows, for every C greater than 0, no matter how small it is, there only exist finitely many Cherenkern classes with topological entropy greater than this constant. And furthermore, the number of such classes vary upper semi-continuously in C1 topology. So it's like no matter every time you fix a threshold, a lower threshold for the entropy, you have a finite number of Cherenkern classes above that threshold. So the only thing that you need to show for the spectral decomposition conjecture is to show that this number remain bounded when C goes to 0. That's the only thing left. But unfortunately, this is not something that we were able to do. So this is the only remaining case for the spectral decomposition conjecture. So you only need to prove the following result. That is, for C1 open dense star flows, every non-trivial Chern current class must have positive topological entropy. Once this is proven, you combine it with our work, and you will have the affirmative answer to Smale's spectral decomposition conjecture. Now, I won't have time to talk about the structure of the proof because the whole paper is well over 120 pages long. And this is only the second part of the paper. The first part of the paper is another one that is also over 100 pages. Um, so I'll skip through most of the proof, but I'll just quickly show you the main tool. The main tool is basically an improved version of the Kleinpaget-Thompson criterion on the uniqueness of equilibrium state. However, their version cannot be directly applied to singular flows for very technical reasons, so we have to make some very substantial improvement over here. We actually needed two improvements. One, get rid of a version of a set shadowing property to make it a bit weaker and so that it becomes applicable to singular flows. And another version that deals with saddle type invariant sets instead of just attractors. So their previous criterion is basically designed for attractors, and you cannot apply it to even hyperbolic saddles. So we have to work around and make that work. But once you have that, we constructed fake foliations on the normal bundle. We discussed the coexistence of actually not just four. I said four on the slide, but actually it is six types of hyperbolic times. Two types characterizing the recurrence to the singular set, and four types characterizing the actual hyperbolicity of the linear Plancks flow. And we want all of them to actually coexist for a certain type of orbit. Normally, the coexistence of Please times is a very subtle issue, but in this case, you can actually make it work due to some very special properties of singular vector fields. And once you have that, you have some kind of distortion control, and this will allow you to prove the bounded distortion property that you need for the uniqueness of equilibrium state if you follow Bowen's work. And then the hard part actually of this paper is to obtain some version of the shadowing property, in which case we choose to work on the space of all ergodic measures. And there's a very, very subtle estimate. In the end, we were able to show the following, basically. So there is actually some sort of compact set. You should think of it as a peasant set for singular flows, where the compact set has very nice hyperbolicity, has very nice transversality, it has everything you want. But at the same time, it is a set that every invariant measure can see. So we showed that there is a very nice compact set with uniform hyperbolicity in some sense, so that every invariant measure that is not a point mass at a singularity must assign a uniform mass to this set. And we kind of use this compact set as a bridge to link certain part of the system to other parts of it. And then this creates some kind of shadowing orbit going from one part of the system to another. And those kind of shadowing orbit will glue different parts of the system together to show that the MME has to be unique. So this is basically the structure of the proof. Now, there are, well, like I said, many, many technical difficulties that you have to overcome, but I'm not going to show you here. There are a large number of conjectures in this field, such as the counting of periodic orbits, the semi-continuity of the entropy, like the classification of the topological structure, and so on and so on. This is a very new and ongoing field in dynamics because the right notion of hyperbolicity was only discovered just 5 years ago. So yeah, for those of you who are interested in this topic, feel free to come talk to us about it. And that's it. Thank you very much.
Well, we thank the speaker. A very interesting talk. Let me stop the recording.